All right, and then the last video I'm going to do is the review of forces, so midterm review for the forces and Newton's laws. The first part of this review has a matching section. I'm only going to highlight a couple of them. I don't want to go through all of them again in detail. So I want to highlight the difference between mass and inertia. So again, mass is what gives an object its inertia. So it's a property of matter that gives an object its inertia. The more mass it has, the more inertia it has, versus inertia, which is an object's tendency to resist its change in its present state of motion, which in this answer choices is B. So when we think inertia, it wants to resist motion. It wants to either stay at rest or stay moving. And this is Newton's first law, which is the law of inertia, which says an object in motion will stay in motion unless acted upon by a net force. An object at rest will stay at rest unless acted upon by a net force. That's Newton's first law. Newton's second law is that F equals ma. That the force will cause a mass to accelerate. Specifically, F equals ma. And we'll be using that equation a lot. And then Newton's third law is G. For every action, there's an equal and opposite reaction. When we talk about the difference between mass and weight, now weight is a force. Mass is a property of matter. Weight is the force that an object has due to being on the Earth's surface. So weight is a force. And then friction, tension, and normal force are all forces. The normal force is this force that's always perpendicular to a surface. The tension is a force that's associated with ropes, strings, and cables. And friction is the motion of a sliding object is opposed by this force. So friction always opposes the motion of an object. All right, so those are just some definitions that you'll want to learn for the concept stuff. Some of the multiple choice questions. You're in a train traveling on a track, and notice that a piece of luggage starts to slide to the back of the train. So you're on the train. The luggage begins to slide backwards. From this, you can conclude what? So if we're on the train and the luggage is sliding back, that means the train must be moving faster than friction can accelerate this. So this must mean that the train is speeding up, and friction can't keep up with that. In question 11, if the bucket of concrete is being lifted with a rope. So if the bucket is being lifted at constant speed, what do we say about constant speed? Well, constant speed means acceleration is 0. So that means if it's being lifted at constant speed, then that means if we look at the free body diagram of our bucket, we got tension pulling it up and the weight of gravity pulling it down, Fg. If it's at constant speed, that means these two forces have to cancel each other out. And that means that they're equal to each other. So the tension in the rope is equal to the weight of the bucket. Remember that it's not equal to the mass of the bucket. Fg is mass times gravity, and it's a force. The weight is a force. Okay. Same idea. If the bucket is being lifted at a constant speed, what is said about the net force on the bucket? So again, constant speed, that means acceleration is 0, which means that my net force, remember from Newton's second law, the net force is equal to mass times acceleration. If A is 0, mass is not, that means that F is 0. The net force is 0. And if the bucket is accelerated upwards, so now it does have a positive acceleration. Again, looking at this free body diagram, now they don't cancel out. Okay, so the tension's pulling it up. gravity is pulling it down. And if it has a positive acceleration upward, my acceleration is up, then that means that this tension force here has to be greater than the weight force. Because that would imply that the tension's pulling more than gravity is pulling on it. And that's why it is accelerating upward. And so here we have that the tension is greater than the weight, which is why it's accelerating upward. The forces don't cancel out like they did in number 11. Okay. All right. Some more concept questions. 14. Now we're talking about a box resting on a floor with friction. So when you see rough floor, that just means that there could be friction. In order to push the box across the floor at constant speed, which implies that acceleration is 0, you must do which of the following: push the box harder than the box pushes back, push with a force greater than the force of friction on the box, push with a force equal to the force of friction on the box, or push with a force greater than the coefficient of friction between the box. So if we want the forces to cancel out, in order for the net force to be 0, because the acceleration is 0, that means that if we push in this direction, then that means that friction is opposing the motion to the left. These forces must cancel out. We want these two to cancel out like they did in number 11 in the back, which means that in order to push at a constant speed, we have to push with a force that's equal to friction. So we want our push. If our push is greater than that, like in part B, it's going to accelerate. And the coefficient of friction is just mu Fn. This guy right here, that's coefficient of friction. And so the force will be greater than the coefficient of friction, but you can't really compare those because they're not the same units. So, but number-wise, it will be larger, assuming the normal force is greater than 1. Anyway, same problem. Boxes rest on a rough floor. So again, friction applies in order to accelerate the box across the floor. So now we want it to accelerate. In this case, we want acceleration to be more than 0, which means there is going to be a net force. Which means same idea as the bucket problem. The push on this has to be larger than friction. So the push has to be greater. So B, push with a force greater than the force of friction on the box. Ben, 50 kilograms, and Jerry, 75 kilograms, are sitting in the middle of an ice rink when they put their hands together and push so that they slide away from each other in opposite directions. When pushing each other apart, who felt the greater force? Right. Anytime it asks about who felt the greater force when two objects are pushing on each other, this is a trick question, right? Newton's third law says that for every action, there's an equal and opposite reaction. That means the force that Ben put on Jerry. So this is Ben. This is Jerry. When Ben pushes Jerry, he pushes him in this direction. When Jerry pushes Ben, he pushes him to the left. And so what we're left with is that the force from Ben, FB, is equal to and opposite the force from Jerry. So again, these two forces, this force and this force are equal. And both slide away from each other because there's not a lot of friction holding them back. Okay. Now, same idea in question 17, but now it says when they slide away from each other in opposite directions, who felt the greater acceleration? So now it's talking about the acceleration, not force. So when we're talking about acceleration, whoever is more massive is going to feel less acceleration. Here we're looking at Newton's second law, F equals ma. If I have, Ben is only 50 kilograms. So he is going to accelerate more because it's a smaller mass. They both experience the same force. So a smaller mass means a larger acceleration. Okay. Question 18, what's the weight of a 100-kilogram object? Just remember weight. This one's just checking. Do you know the definition of weight? Weight is the force of gravity, or mg. So it's 100 times 9.8. (980 newtons). Okay, now for the free response section, again, thinking back to the midterm, there's going to be one force question on the midterm. So we're going to do a couple examples here. I've got 1, 2, 3, 4 examples in the packet. And so it's going to be some combination of these for the free response. So we're going to look at question 1, which is vertical motion. It says a 3,200 kilogram junk car in a junkyard is being lifted off the ground, moving vertically. Draw a force diagram for the car. So free body diagram, we have that the tension is pulling it upward. And we have that gravity is pulling it down. In part B, it says find the tension. So what is the tension in the cable? If the car is being accelerated at 1.5 meters per second. So when you're doing these questions, if it's moving vertically, then the idea is, we're starting with Newton's second law, F equals ma. But the force, this is the net force. So the net force is going to be all of my forces pulling it up, which in this case is just tension, minus all of my forces pulling it down, which in this case is just gravity, is equal to my mass times my acceleration, which is 1.5. And so here I'm just going to plug in and solve for ft. So I got ft minus, remember, fg is mg. So this is 3,200 times 9.8. And that equals 3,200 times 1.5, which means that ft is 36,160 newtons. And so that's how you can solve one of those problems with tension and weight. When it's vertical, it's the forces going up minus the forces going down equals ma. Okay. On number 20, an empty box is suspended from the ceiling with a cable. So same idea. We have the box and it's being held up by tension and it's being pulled down by gravity, by its weight. And so the force diagram is exactly the same. Remember, the weight is mg. And this time it says the cable can withstand a tension of 9,500 newtons. How much mass can you put in the box before the cable will break? So here, this max tension is 9,500 newtons. It's not accelerating, right? It's at rest. It's being suspended from the cable at rest. So the acceleration is 0, which means that when I think about the forces going up minus the forces going down equals ma, a is 0. So this right-hand side is going to be 0. Unlike in this one where it was accelerating up, we set it equal to ma here. We didn't cancel that out. Here we're going to make that equal 0. That's really key there because the acceleration is 0. Okay, so now I can plug in 9,500 for my max tension, and I want to solve for how much mass I can put in this. So m times 9.8 equals 0, and I'm just going to solve for m. I'm going to subtract over the 9,500, so I'm going to have negative 9.8 m equals 9,500, or negative 9,500, and then divide over the negative 9.8, which will give me a maximum mass of 969.4 kilograms before the cable snaps. Okay. So those are examples of vertical problems. Now, the horizontal ones are going to be ones like 21, where they're already on the ground, and then there's some amount of friction, or maybe there's no friction. And there may be some force on this thing. So for number 21, it says a 25 kilogram box is sliding to the right on a frictionless surface. So in this case, we don't have friction. And then it encounters a rough patch. So we have no friction. It hits a rough patch. That means there is friction. And that's what causes it to start to slow down. So the acceleration will be less than 0. It'll be a negative acceleration. Draw a force diagram for the box while it is on the rough patch. Rough patch means we have friction. So it's on the ground, so we have friction slowing it down. It's on the ground, which means we have a normal force pushing it up, and we have its weight pulling it down, 3 forces. Part B, calculate the normal force on the box from the rough patch. So what is Fn? Well, in this case, Fn has to be equal to Fg. These two have to be equal to each other. And the reason that is we can go through that same idea from the last two problems. Fn minus Fg, forces going up minus the forces going down equals ma. But in this case, it's not accelerating in the y direction. It's not going up or down. It's accelerating to the right. So that means that these two forces are equal to each other, which means that Fn is equal to the mass times 9.8, which is 245 newtons. All right, and then part C, if the coefficient of friction between the box and the patch is 0.08, so now they tell us this mu is 0.08, calculate the resulting acceleration. So now we need to look at just the x direction force, which is friction. There's nothing to the right here. And so when I'm doing a horizontal problem, like when I was doing vertical, we did top forces to the top minus forces to the bottom. When you're doing horizontal, it's forces to the right minus forces to the left. So the forces to the right, there are none. The forces to the left, so we did minus, are friction. So forces right minus forces left equals ma. And we want to calculate the resulting acceleration a. So we have negative friction. Friction, remember, the equation for that is mu times the normal force equals ma. And I'm going to plug in. So for mu, it's 0.08. Normal force we found as 245. And mass is 25. And so now I can solve for the acceleration, multiply it, and then divide, and I get negative 0.784 meters per second squared. And so you might be asking, well, why was A not 0 here? Well, because it was equal to 0 over here, so why didn't we just do the same thing and set it to 0 over here? Well, it's because we're working in the x direction. So over here on the left, we were working the y direction. The thing was not accelerating up or down. But on the right-hand side, it is accelerating. It is slowing down. So the box is actually slowing down to the left. And so we do actually have a negative acceleration. Right? And then the last example on the review, number 22. A horizontal rope is used to pull an 8,500 kilogram train car down a track at constant speed. Constant speed, that's important. Draw a force diagram for the train. There's our train. We have the pole. We have the normal force. And we have gravity. Is there friction? Well, there has to be. If we have a constant speed, then that means that the acceleration is 0, which means if this was as is, then this force of the pull would accelerate it because there is nothing canceling it out over here. Which means there has to be a friction that's equal to the force that we're pulling it with so that these two can cancel out. So that the force of the pull is equal to friction, and then the normal force is equal to gravity. Okay. So it says in part B, calculate the normal force on the train from the car track. Well, those two have to be equal to each other. Or another way of writing it, just to be consistent, the force is going up minus the force is going down equals ma. In this case, the y direction acceleration is 0. So my normal force is Fg, which is going to be mass times gravity, or 8,500 times 9.8. So Fn is equal to 83,300 newtons. Okay, and then in part C, it says if there's 3,100 newtons worth of tension in the cable pulling the train car, what is the coefficient of friction between the train's wheels and track? So in this case, they're telling us tension, and they're asking us to figure out what mu is. I mean, they could have also given us mu and told us to figure out tension. The method would be the same. So we're looking now at the red forces. The pull to the right minus friction to the left equals ma. Now, this is the same thing we did right here. The force to the right, there was no forces to the right minus friction equals ma. So I'm really just rewriting that. But this time, it's the pull force. So the pull force minus friction equals ma. Now, we know that it's moving at constant speed. So A is 0. And so we know these two forces are equal to each other. It told us that the tension, the pulling force, is 31,000. Friction is mu Fn. And so we can simply solve for mu. 31,000 equals mu times Fn, which was 83,300. We found in part B. And so mu is 31,000 divided by 83,000, or 0.37. Okay, and that's it. Remember, there's going to be a free response question on forces, so make sure you study these ones and know how to solve them.